Hey everybody, so here's lecture 27, only 3 more lectures to go, 27, 28, and 29. Optics, geometric optics, no more magnetic fields, electric fields, cross products, calculus, simple geometry, real practical material. Those of you who are interested in photography or imaging of any kind, hopefully will find this to be of interest. So this is going to be a kind of a short lecture here today because I'm going to spend most of the time talking about the applet that is really a better tutorial tool for this. So the reading quiz real quick. A spherical concave mirror. A spherical concave mirror is a mirror that bends this way with the mirroring surface, the silvering on the back. Okay. That's to be contrasted with the plane mirror, which is like a mirror on your wardrobe, where you form an image behind the mirror. Okay, and that's a virtual image because the rays don't actually go through the point. In contrast, a spherical concave mirror makes an image that's in front of the mirror, and it makes it halfway to the center of curvature. If this is a big circle here that looks like this, and this is the center, then a distance half the radius of curvature, here's the radius of curvature of the mirror. This focal length distance between here and the front surface of the lens, the focal length is 1/2 the radius of curvature. We'll show you how that focuses here in the lecture. Rays that converge to form an image actually pass through the image. If that's true, the image is said to be a real image. This makes a real image, a planar mirror makes a virtual image. Okay, so here's that again. If I take a circular spherical mirror, a mirror that forms part of a perfect circle coming around here, this is the radius of curvature, then if I have a ray that comes in parallel to the axis of the mirror, coming here, then by the laws of incidence and reflection for a locally surfaced plane mirror, this angle of incidence is equal to the angle of reflection. Okay, so the ray comes in here and it makes an angle theta there. It bounces off going this way and it focuses there. That's the focal point. No matter where I do this on the mirror, all of those rays focus at that same point. Okay, so there are 3 principal rays that define an image. We only need 2 of them. Actually, there's a 4th one. So here's the meaning, how you interpret this thing. Okay, here's an object sitting here. We usually draw that with an arrow that looks like that. Here's the object. This distance between here and the mirror is DO, the object distance. Where we form the image down here is going to be the image distance. So this is DI from that surface of the mirror to where the image is. Here's the object, and here's the image sitting here, down here. 3 properties of principal rays. Ray 1 comes into the mirror from the object, strikes the mirror, and it goes through the focal length. So follow the arrows. The ray is coming in here and going out that way, and it proceeds somewhere along this line here. So somewhere the object at the top of that image is going to be located. We need to intersect at least one more ray to locate exactly where. Okay, ray 2 goes through the focal length. Okay, so instead of going parallel, it goes this way. Okay. But that's kind of the opposite effect of the previous case. So if it goes in this way, if it goes through the focal point, it's going to come out parallel. So it goes there. Okay, where those 2 rays intersect, this ray and that ray, that's the image distance. So here's the image. Okay, we can check that with one more ray. Okay, principal ray 3 goes out perpendicular to the mirror and it comes back on itself. So that's this one here. It goes from the object to the mirror, then it doubles back on itself because it had a 90-degree angle of incidence. It's going to have a 90-degree angle of reflection. So it doubles back on itself, comes back this way. All 3 of those rays then converge here. So here's the image. Okay, Now, there are three ways we're going to define the nature of this image. Whether it's upright or inverted, its magnification, whether it's bigger or smaller than the image, and whether it's a real or virtual image. What are those three properties here? Those three properties for this one are the image is inverted. This object was right side up, the image is upside down. This one happens to be, for this configuration, a magnification which is greater than 1. The image is bigger than the object. And it's a real image because the rays actually go through there. Okay. In contrast, if you have a plane mirror, okay, and if I stand here with an object, you know that the image forms back here behind the mirror. Okay, it's a virtual image. Okay, I'm doing this kind of quickly, guys. Okay, all right. So from that kind of construction, you can calculate the properties of a concave mirror, and here is that derivation. Okay, here's the same configuration I drew on the previous page, and I start taking similar triangles. Okay, I take this triangle here and that triangle there. Those are similar triangles. That says the image height compared to the object height, or the object over the image, is the same as the ratio of this triangle here, DO and DI. And I put a minus sign there because the image is upside down. Okay, that's one parallel set of similar triangles. There's another similar triangle that says this one here, HO over HI. The distance HI and HI is OF to FA. OF to FA, okay, and that's this equation here. Put all those together, and I'm doing this real fast, okay. Here you've got the fundamental equation of what's called the mirror equation or the lens equation, 1 over DI plus 1 over DO plus 1 over the focal length, okay. If I know the focal length, I can get the object or the image distance from this simple equation. It's reciprocal, okay. This is true for lenses, mirrors, uniformly. The magnification is HI over HO, and from that triangle, then DI over DO is there with a minus sign. I'm going to ask you to read this on your own. I'm going to ask you to look at these special cases for object distances less than the focal length, greater than the focal length, and what do you get for a convex mirror. Rather than spend some time talking about that here, okay, I'm going to jump then immediately to the applets that give you a way to play with this on your own. Those applets on the next page of your handout, it talks about Davidson Optics Bench. That applet no longer runs given the paranoia about security in Java systems, but I found this website now that has an Optics Bench, and that I'll link that in the Moodle reference to that. So the next part of the lecture, after you've gotten to this point now, read the applet, look at the applet video, and we'll pick the lecture up there. Okay, see you when you get to the next video.